0, acceleration in the y is going to be negative g due to gravity. So, in projectile motion, this is 0, meaning this entire term goes away, and this entire term goes away. Also, in y, acceleration is negative g, so we just put in negative g here, and negative g there. And I recognize the problem set was really long, just to emphasize how important this section is. So not only am I going to put projectile motion problem on the quiz tomorrow, there will also be projectile motion next week as well. Now if I put if I put the same topic in 2 consecutive quizzes, that's me trying to convince you guys this is very, very important. Okay? So this, if there's any single type of motion that you guys really want to get down in terms of studying kinematics for the midterm, this is it. Because if you're able to do that, you can do one-dimensional kinematics, no problem. But if you spend all your time thinking about one-dimensional kinematics, when you add on a different level of complexity, then you're going to come across a brand new world. But 2-dimensional kinematics is more complex, so if you master that, and you remove a layer of complexity, well, it becomes easy, and you already mastered that too. So just study for projectile motion. This is going to be the most important section. And this is pretty much where we left off. Was doing some examples. Oh, and we also did relative motion as well. All right. So what we're doing today is a different type of 2-dimensional kinematics. And this tends to be the harder of the two. So harder than projectile motion. So this is 2D kinematics. And the type of motion we're going to be talking about is what is called circular motion. Circular motion. Now let's first begin by defining what circular motion even is. As you can guess, it is an object whose trajectory is what? Yeah, is indeed a circle. An object whose trajectory is a circle. And one of the important features about a circle is that it has a characteristic length called the radius. So with radius r. So if we were to, let's say, sketch out a schematic, let me try to draw actually a decent circle. I guess good enough. The radius extends from the center of the circle as such. Now, when the object is traveling in a circle, we can also draw the velocity vector, and it would be what is called tangent to the circle. It barely touches the circle itself, so it's just smoothly touching. And of course, if the particle was on this side, the velocity would be straight down, and if the velocity was over here, then it would be slightly at an angle upward in this direction. So note is that V is always tangent to the circle. Now you might think, man, is this even worth writing down? This is so obvious. Yeah, you would think so, but many people make a mental error. The reason why I need to say this explicitly is because people begin confusing circular motion with what is called rotation. They are not the same thing. This is not rotation. So what is the difference? What is the difference between circular motion and rotation? In circular motion, let's say an object that looks like this is just moving along this path. It's moving along a path, so it starts here and then it's moving in a circle like this. Whereas rotation, you would have an object like this, and the entire object is spinning around. These are not the same thing. Now, they are related, and we will get to rotation much later, but it's not the same thing. Now, one of the ways that these are related, just to show you how they are, is let's say there's an object that's going to be rotating. And I label a mark here. When this object rotates, what shape will the X end up making? Right, that will make a circle, but it would only be this point that's making a circle. The entire object is not making a circle in and of itself. Okay? What we are talking about is not rotation, but the trajectory looks like a circle. That's what we actually care about. So not rotation. But, so let me underline the trajectory, that is the key. The trajectory is circular. Now in circular motion, there's going to be a special type where the speed is not changing. So if speed is constant, this is defined as what is called uniform circular motion. Uniform circular motion. And here we will call that UCM, or uniform circular motion, UCM. Now, I mentioned that circular motion tends to be more difficult than projectile motion. That is true, not because the problem's actually harder, but because we no longer use X and Y coordinate system. That's the reason why it's harder. Instead of X and Y, we have to begin using different notations. And another reason why it's harder is when we did projectile motion, we only looked at 3 different things: position, velocity, and acceleration. In circular motion, we're going to look at 10 things. That's also why it's a little bit more difficult. It's just a little bit more mentally taxing. So let's begin to compile what those parameters are. The first one is the radius. Radius R. Okay, so that one's pretty simple. It's just how large the circular trajectory is. That's just that characteristic length scale of the circle that you are working with. The second one is what is called the period, T. This is the duration for a particle to complete one revolution. Now, in other words, this is a duration for a particle to travel what distance? The circumference. The time it takes for a particle to travel the circumference. Who remembers the circumference equation? 2 pi, not 2 pi r squared, just 2 pi r. 2 pi r. So meaning, remember what the definition of speed is. V is defined as distance over time, or not time, duration. Hopefully this rings a bell. Speed is distance over duration. What distance is it traveling in a period? It is 2 pi r. So the speed is 2 pi r over the period t. So as soon as you're given a period, you have a general sense of how fast the particle is moving, because you would also know the radius as well. And so once you're given the period, you immediately know the velocity. So that's the second parameter. We have, okay, we technically have 10. I forgot to number one of them. Let's get to the next one. So in projectile motion, for position, we used x and y. In circular motion, we're going to be using what is called angular position, and we give that the notation theta. Theta. So, in circular motion, Cm, there is a better way, or better method, of specifying position. So instead of x and y, use what is called r and theta. And this is the hard part. Beginning to think along these lines when your minds are so accustomed to thinking about x and y. This is the hard part. So, in a normal coordinate system, let's say we have this circle. We have this circle. At this point, we would have a certain x, let's call that x1, and we would have a certain y, we'll call that y1. At a later point, let's say over here, we have point x2 as well as y2. Right, you guys follow? When an object is moving, you see both the x and the y are changing. Do you guys see that? Both the x and y are changing. This is very, very inconvenient. Because you're moving in a circle, is the radius changing? And the answer is no, the radius is constant. So instead of changing two things, if we use r and theta, we will indeed only be changing the theta. This is the reason why r and theta in circular motion is much more convenient. So you have this circular motion. There we go. So if it's here, you're at a certain r value, but we'll just call that theta 1. If you're here, you're still at r, you're just at theta 2. So one thing changes as opposed to two things are changing. But let's see if this actually even makes sense, if this is even adequate. How does the x and y system work in the first place? So, when we specify an x and y coordinate, let's say we specified x1. Then we are saying we are including everything right here at that x1 vertical. And to get this point, we would have to specify y1 meaning we include everything right here. And it is the intersection of the two that actually establishes our point. So you see, you need two pieces of information to identify the point, right? Is that correct? And that is also the same case with r and theta. When you specify the r, what you're specifying is you're specifying this circle. If you specify a slightly smaller r, it will be this circle, but in this case, we're specifying this r, so you're specifying that information. And then when you specify theta, you're specifying this line. And where do they intersect? At this point right here. So that's how the r and theta works. So when you specify a theta, you're specifying some angle like this, where everything along that line will be considered. When you specify the radius, you're actually specifying a circle. And the intersection of the two ends up being our point. Okay, that's a lot of drawing out there. So let me get rid of a few things. Okay. So here, theta is defined as the angular position. It's just where along this angle of a circle does it actually exist? And for this, we actually need to revisit a convention. By convention, positive is counterclockwise. 0 is positive x-axis. So the x-axis would be right at that line right here. So the theta is just giving us, okay, what angle is it actually existing? But sometimes we don't care about the angle, we actually care about what is the distance from here all the way up to here, right? What is the physical distance between those two? And for that, this is the one that I forgot to number. You guys can call it number 4, that's fine. But this is what is called the arc length. Arc length S is defined as the total distance total distance made by theta. It's the total distance of the actual circle itself associated with theta. So on this graph, this in the green would be our arc length S. It's actually the part of that circle. And this is indeed related, you can see, to theta 1. So these are related, and they're related in this fashion. S is going to be R times theta. And here, theta has to be in radians. Yeah, Maddie.
So if we have two spots in the circle that are the same angle width, are they going to have the same arc length
Correct.
as well? Okay.
Yes. So theta has to be in radians. I know everyone loves radians, right? Well, radians is actually more fundamental than degrees. Yeah, question.
What does it say there under angular position?
In circular motion, in cm?
Uh,
Oh, here?
yeah.
Oh, convention.
Convention positive is,
Counterclockwise.
okay.
CCW. So here, if you want to get the arc length, you have to use radians. There is no other way. You can't use degrees. It doesn't work. Because degrees are for losers. No, I'm just kidding. It's because radians is more fundamental. Radians is more fundamental. So let me ask you guys a question. Where does radians come from in the first place? What makes a radian a radian? What is 1 radian? And does anybody know? Anybody know the history of circles and such? The radians come from, let's say you have a circle of radius r. What angle would you get if you take this radius and you plop it on a line, or plop it on the circle itself? So instead of, you take this radius, let's say it's in red, and then you map it onto the circle, what degree do you think you'll get? This is equal to 1 radian. That is what a radian means. It is the angle made when you take the radius of the circle and then you plop it onto the circle itself. That is the angle that you get. And it is this relationship that allows the radian to be used to compute this. It is the physical length associated with the angle that you're traversing. Degrees does not have this relationship. What is 1 degree? Has no relationship to a radius whatsoever. Okay, so this is why, if you want to use this, you have to be using radians. So you can think of, radians as the SI unit for angle. Yeah.
Is it possible to convert between the two, radians to degrees?
Yeah, so in one circle, how many degrees are there?
Wait, no, 360.
360. In one circle, how many radians are there? Anybody know?
2 pi?
2 pi is correct.
Oh,
So 2 pi radians is equal to 360 degrees, or I simply remember pi is equal to 180 degrees. So pi radians is 180 degrees. That is the relationship. Or you can do second mode on your calculator and then just hit the radians button. I just remember to do that. Although I actually just end up doing this because converting back and forth actually takes longer. All right, so that's a little interesting factoid about circles, but let's continue on with circular motion. So, you can think of the theta would be the angular position. You can think of the arc length as tangential position. You can think of it as what's called the tangential position. But this will become relevant in just a moment. Tangential. Tangential. Now let's look at the fourth one of very high importance is angular velocity. Angular velocity. It is the Greek letter omega. Not a W, omega. Omega. this is the answer to the question, how fast is theta changing? How fast is theta changing? So remember, the velocity was delta r, or change in r over duration, the change in position over time. Likewise, omega is going to be delta theta over delta t. So there is an analogous relationship between velocity and angular velocity. Just like how the velocity was the slope of the position versus time, omega is the slope of theta versus time. Now, omega has units of radians per second, or another one you might see is degrees per second, or the more common one would be RPM. Let's make sure we all understand what RPM is. What is it? Huh? Okay, rotations or revolutions per minute? Which one? It's actually the same, but technically it's revolutions per minute. A rotation is a revolution, that's true. But what did I say? Circular motion is not rotation. It's a revolution. But it conveys the same idea. Revolutions per minute. So whenever you see units like this, you immediately think of omega. Now with this definition, oh yeah, question.
Does that say theta over s? Next to radians over s?
No, degrees
Oh,
over s.
degrees.
Degrees over s. Now let's come back to something we already discussed, the period. It is defined as a duration for a particle to complete one revolution. One revolution. We just discussed that a circle